happening. We dedicate this lesson to Jordan and Emma, who have missed this class, so this one's for you. You can watch this one at home. Right. Now, pressure. We're going to look at pressure in terms of Newton's second law. Now, we know that pressure is equal to the force per unit area. The unit's newtons per metre squared. And we know that the particles of a gas exert the pressure when they hit the walls of the container. We also know that Newton's second law is equal to force times mass times acceleration. Now, if we have a force of a particle hitting the wall of a container, we have to have Newton's second law implied in that action. Now, if I have a particle, my particle is travelling forwards, hits the wall of the container, and then bounces back. We say that this collision is elastic. The term elastic means that no energy is lost. If I have V going in as my V1, I have to have minus V coming out as my V2. If I have a positive direction going in, I have to have a negative direction coming out because we are dealing with vector quantities. I've just put a little note just there to explain that. So if we now take the change in velocity, which admittedly we would normally define as V2 minus V1, however, this time I'm going to define it the other way around, simply to get rid of the minus sign. I don't need that at the moment, so I'm just going to get rid of that. I now get V minus V over t, and my change in velocity is 2V over t. If I now plug this into Newton's second law, we get m 2V over t, bring my 2 outside of the brackets, whereby we get 2mv over t. Therefore, we can see that the force exerted from the collisions is a rate of change of momentum. mv is the momentum, and therefore force is a rate of change of momentum, in this case of the particles. And that, ladies and gentlemen, is the origin of pressure.